Hello, my name's Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering, and this is a little review video on partial fraction expansion. And so the reason why partial fraction expansion is important for us from a circuits analysis context is that we are going to be using Laplace transforms a lot to determine the transient and steady state response of circuits. And to avoid using integrals as much as possible, I am going to teach you how to rely fairly heavily on a table of standard Laplace transforms. In fact, all of the Laplace transform problems I'm going to give you can be solved with this table and not with doing the actual integral-based inverse Laplace transform. And so this is the table that I've posted on the course website, and if you don't have access to that, if you're not registered in the course, this is a very standard table of Laplace transforms. And you can see we have terms like 1 over s plus a corresponding to an exponential in the time domain, 1 over s being a step function, 1 over s plus a squared as being an exponential multiplied by a time variable, and so on. And so our objective when we do Laplace transform analysis is to come up with an equation that can be easily inverse transformed with this table. Now, one of the challenges we're going to find is that when we do circuit analysis, we're often going to come up with expressions that are a function of s, because we're working in the Laplace domain, where we have a numerator that's a function of s and a denominator that's a function of s. So far, that's not really a problem. The problem arises when we have an expression that doesn't really show up in our Laplace transform tables. And so an example is when we have a denominator that consists of the product of a number of terms. And this is, whoops. And this is something that's going to come up. This form of an equation is going to come up a lot when we solve our circuit problems. And so there is no term in the Laplace transform table that includes a bunch of products of these s plus p terms in the denominator. And so the purpose of partial fraction expansion is to allow us to separate this denominator, basically. So we're going to take this equation and we're going to write it in the form of a constant k1 over s plus p1 plus a constant k2 over s plus p2 all the way up to kn over s plus pn. And the purpose of partial fraction expansion is to allow us to determine the value of these constants. Just as a little bit of terminology, we call the values of p1, p2, all the way up to pn the poles of this function. And the reason for that is when, for example, s is equal to minus p1, we have a 0 on our denominator, and our function spikes up to infinity. And so if you were to plot this versus s, and as you got closer to negative p1, the value of the function would start to jump up towards infinity, and it looks like a pole, basically like a big tall pole. And so that's where that term comes from. It's not, that terminology is not super important for us in 343, but as you do more advanced circuits analysis classes, filter analysis classes, signal processing classes, the term poles and correspondingly the term zeros is something that you're going to hear as well. The zeros are the values of s that cause the numerator to be equal to 0. So that's not super central for us right now, but it's something that you will run into later on in your learning So the first situation that we're going to discuss is the case of unique poles, where, and the way that I've written this is pi is not equal to pj for any I not equal to j. So basically this means when I is not equal to j, we're comparing any two different poles, and we're saying that they can't be the same. So this is unique. So that means p1 is not the same as p2 or any of the other ones, and p2 is not the same as any of the other ones, and so on. And so for this case, it's possible to determine the value of these constants. So let's say the value of constant ki, where I is equal to 1 or 2 or n. We can figure out this constant by basically taking our original function, f of s, right? So this is our original equation, this one right here, multiplying it by s plus pi, right? So if we wanted to determine k1, we would multiply the equation by s plus p1. If we were determining k2, we would multiply by s plus p2. Then we set the value of s equal to minus pi. And that allows us to solve directly for the constant. It's not like, if you're not familiar with partial fraction expansion, looking at this, it's not immediately obvious why this equation is the way that it is, but there is a fairly straightforward proof for it. So if you Google it, or if you look in most sort of standard circuits or differential equation textbooks, they'll give you a quick proof for this, and you can see where this comes from. And so what I'd like to do is proceed with an example. So I've actually already written this example out, and I'm just going to sort of slide this sheet of paper down and talk about each part of the example as we work through it. If I do go a little bit fast for you to write everything down while I'm discussing it, remember you can pause the video, right, and just write things down. So let's do an example where our equation f of s is equal to 4 divided by s times s plus 1 times s minus 4. And so another way to write this, obviously, rather than just having this s, is s plus 0. And that means that we have 3 poles. The first one is s equal to 0. So if we have s equal to 0, this term goes to 0, and the function goes to infinity. Our second pole, p2, is equal to minus 1. That causes this term to go to 0. And the third pole, p3, is 4, which causes that term to go to 0. And so our objective is to write this equation as k1 over s plus k2 over s plus 1 plus k3 over s minus 4. And the purpose of partial fraction expansion, again, is to determine these 3 constants. All right, so let's start by determining k1. So to determine k1, we take the denominator, basically s, or we can write this as s plus 0. We multiply the original function by it, and then we set the value of s equal to the pole. And so that means we take our original function, 4 over s times s plus 1 times s minus 4, multiply it by s, so that means, as I've indicated, these two terms cancel, and then we set s equal to 0. So that gives us 4 over 1 minus 4, or in other words, it gives us a value of minus 1. Let's do this now for k2. So k2, or to solve for k2, we take the denominator and use it to multiply our original function. We set s equal to minus 1, which is our pole. Now in this case, s plus 1 cancels the s plus 1 in the denominator. We have 4 over s times s minus 4. And we set, again, s equal to minus 1. And when we do that, we get 4 over minus 1. That corresponds to that term. Minus 5, which corresponds to this term, right? Minus 1 minus 4 is minus 5. And that gives us a value of 4 over 5. Finally, to solve for k3, we multiply f of s by the denominator s minus 4. We set s equal to 4. The s minus 4 terms cancel. Setting s equal to 4 gives us 4 over 4 times 5, or in other words, 1/5. And so this is the procedure. And so this means that our final equation can be written as 4 over s times s plus 1 times s minus 4. This is our original equation. And this is equal to minus 1, which was our value for k1, 4 over 5, which was our value for k2, and 1 over 5, which was our value for k3. These can be negative, but it just in this case, or they can be negative, like, for example, the minus 1, and then these two terms, of course, are positive. So sometimes doing this partial fraction expansion, because it is a fair bit of algebra, it's easy to make mistakes. And so there is one kind of handy way to check your work, and that is by substituting an actual number value in for s, and making sure that the numerical value of this equation equals the numerical value of this equation. Obviously, you can't choose one of the poles, right, because you get infinity, but choose something that isn't a pole. So for example, if I use s equal to 2, we can calculate a value for the left-hand side and the right-hand side. And that's what I've done here. So if we set s equal to 2, then the left-hand side is equal to 4 over 2 times 3 times minus 2. And that's equal to minus 1/3. And again, this is the s term. This is the s plus 1 term. This is the s minus 4 term. And that value is equal to 1 over 3. We can also plug this into the right-hand side of the equation. So this is minus 1 over s. So we've got s equal to 2. This is 4 over 5, which was our value for k2, multiplied by 1 over s plus 1. So that's where we got the 3 from. And we have 1 over 5, which was our value for k3, times 1 over 2. Now we have a negative sign here. That's because this value is actually minus 2. So this is the s minus 4 term, when we plug in the value of 2 for s. And I just took that negative out there. And so if you work the fractions, common denominators, all that kind of stuff, you end up finding out that the right-hand side is equal to 1 over 3 as well. And we know that our work is correct. Okay, the next case I want to talk about is when our poles are the same, or when we have all of our poles the same. And the way we write that equation, again, we have a numerator that's potentially some function of s. We have a denominator, also some function of s. And in this case, I'll do the case where we only have basically one repeating pole. We have s plus p to the n. And so we have, if n is 2, then this is squared, and we've got, a pole that repeats itself twice. If it's cubed, then the pole repeats itself 3 times. And the way partial fraction expansion works for repeating poles is we actually kind of have an ascending series where we have k1 over s plus p, which is just like raising it to an exponent of 1, plus k2 over s plus p squared, plus k3 over s plus p cubed, all the way up to kn over s plus p to the n. And so when you've got repeating poles, you can use this kind of approach for partial fraction expansion, but it is a little bit of a pain because you do have to, as it turns out, take the derivative of this function of s, which isn't always that easy because you're messing around with the chain rule and all that kind of stuff. And so instead, what we're going to do is we're going to use a different method called the algebraic method to solve this particular equation. So the best way to illustrate how partial fraction expansion works with the algebraic method is really just to kind of work through an example. So let's do an example where we have a numerator that's equal to 5 times s and a denominator that's equal to s plus 2 cubed. So our pole is equal to minus 2 because that's the value that makes this denominator 0. And the pole repeats 3 times because it's cubed. And so the partial fraction expansion would be k1 over s plus 2 to the 1, k2 over s plus 2 to the 2, and k3 over s plus 3 to the 3. Now, the way the way that the algebraic method works is basically you take the denominator here and you multiply both sides of the equation. So we're going to take s plus 2 cubed and multiply it by our original equation. And we're going to multiply the left-hand side of the equation by s plus 2 cubed and also the right-hand side of the equation by s plus 2 cubed. And so obviously when we multiply the left-hand side of the equation, s plus 2 cubed on the denominator is going to cancel, and we're left with just 5s. Right? So this 5s represents the left-hand side of this equation. On the right-hand side of the equation, we have s plus 2 cubed times k1 over s plus 2, s plus 2 cubed times k2 over s plus 2 squared, and so on. And of course, we're going to get some canceling here as well. So this s plus 2 is going to get canceled, and this is going to reduce to squared. This s plus 2 squared is going to cancel, and this is going to just be s plus 2. And of course, s plus 2 cubed is going to cancel s plus 2 cubed there. And so that's what we get. So our equation 5s is equal to s plus 2 squared times k1, s plus 2 times k2, and then just k3. And so what I'm going to do is I'm going to expand out these brackets. So we have s squared plus 2s plus 4, s plus 2, k2, and so on. And the next thing I want to do is group all of the values of k that are multiplied by s squared, all the values of k that are multiplied by s, and all the values of k that are just sort of sitting around and not multiplied by s at all. And so there's only one value of k that's multiplied by s squared, that's k1. When we look at the terms that are multiplied by s, we have 2k1 plus k2, and you can figure that out just by writing this all out. So, for example, we have k1 times 2 times s, right? So that's where the 2k1 comes from. Then we have k2 times s, and so that's why we have k2 right there. And then the terms that are just kind of hanging around, not multiplied by s, are 4k1 plus 2k2 plus k3. And again, still all of this is equal to 5s. And so now how do we solve for these values of k1, k2, and k3? Well, we can write k1 equal to 0. The reason why we can write that is because there are no s squared terms on the right-hand side of this equation. There's only 5s. And so k1, in order for this equation to equal this equation, k1 has to be equal to 0, right? So we know k1 is equal to 0. And this term actually doesn't even show up. We know that 2k1 plus k2 has got to be equal to 5. Why is that? Because the terms that are multiplied by s have to equal the terms on the right-hand side that are multiplied by s. So 2k1 plus k2 has got to be equal to 5. And so that allows us to solve for k2 equal to 5 because we know k1 is 0. And finally, this 4k1 plus 2k2 plus k3 has got to be equal to 0. The reason for that is there's no other term on the right-hand side of this equation. The only term that we had was multiplied by s. There are no terms over here that are not multiplied by s. And so this has got to be equal to 0. And if we plug in our value for k1 and k2, we know that k3 is equal to minus 10. So our final partial fraction expansion was k1 is equal to 0, so this term disappears. k2 is equal to 5, so we have 5 over s plus 2 squared. And k3 is equal to minus 10, so we have minus 10 over s plus 2 cubed. And so again, just like before, we can check our work. And so what I've done is I've substituted a value for 1 in for s. And so when we do that, we have 5 times 1 over 3 cubed, or 5 over 27, is equal to 5 times 3 squared minus 10 times 3 cubed. And so if you work the fractions, you end up getting equality. So we know that the work is correct. And the final case I wanted to talk to you about is where we have the case of mixed poles. And mixed poles refers to the situation where we have some repeating poles and some poles that are unique. And so in this example, we have a pole, this is equivalent to s plus 0, so we have a pole at 0, s equal to minus 1 is a pole, and s equal to 2 is also a pole because all those values cause our denominator to go to 0. But the s minus 2 term repeats itself twice. And so the way that we express this using partial fraction expansion is that the unique poles appear only once, and they get their own coefficient, so k1 over s, k2 over s plus 1. And then the repeating poles just have sort of an increasing pattern, just like they did in the previous example. So we start with s minus 2 to the 1, s minus 2 to the 2. We stop there because our maximum exponent is 2. But if this was cubed, then we would have plus k5 over s minus 2 cubed. And so I'm going to use the algebraic method to solve for the values of k1, k2, k3, and k4. So I use the algebraic method for mixed poles as well as just repeating poles. And so we take our denominator and we multiply it by our equation. Of course, when we do that, the denominator cancels on the left-hand side and we just have 12. So 12 represents the left-hand side after the denominator is canceled. And then when we multiply the right-hand side, I'm skipping a few steps here, or I'm probably skipping a step here, but when we multiply by the denominator, the 1 over s cancels the s term, and we only have s plus 1 times s minus 2 squared. The s plus 1 cancels the s plus 1 here, and we have only s times s minus 2 squared. The s minus 2 cancels just one of the s minus 2 terms, so we have s times s plus 1 times s minus 2. And finally, the s minus 2 cancels this term, and so we have s times s plus 1 times k4. And after that, we proceed exactly the same way as we did in our previous example. So I expand out these brackets, and so we have, this is what is multiplied by k1, this is what's multiplied by k2, and so on. Then what I do is I group all the values of k that are multiplied by s cubed, all the values of k that are multiplied by s squared, and all the values of k that are multiplied by s, and then the remaining values of k that are just hanging around. This has to equal 12. Since there are no s cubed terms on the right-hand side, we know that all of these terms, k1 plus k2 plus k3, has got to be equal to 0. Since there are no s squared terms, minus 3k1 minus 4k2 minus k3 plus k4 has got to be equal to 0. Since there are no s terms, this equation has to be equal to 0. And since this term hanging around, since 12 is not multiplied by any value of s and this value is not multiplied by any value of s, 4k1 has to equal 12. And so what I've done here is I've kind of partially solved the equations, I guess, which maybe wasn't the most clear thing for me to do. But because 4k1 is equal to 12, I know that k1 is equal to 3. Because k1 plus k2 plus k3 has got to be equal to 0. and k1 is equal to 3, I know that k2 plus k3 is equal to minus 3. Here I did the same thing. I've got k1, k2, k3, and k4. I substituted in the value for k1, so k1 equal to 3, so that's why this equation is equal to 9. And finally, this equation also has to be equal to 0, and I wrote that one out just as normal. I didn't substitute in k1. And so if you solve these simultaneous equations using, maybe a matrix calculator or MATLAB or just plain old algebra, these are the values that you get. And if you want to, you can substitute in a value for s and verify that both sides of the equation are equal.